Electrolysis is a process by which a non-spontaneous redox reaction is made to occur by the use of an external power source that produces a flow of electrons, or electricity. The direction of the flow of these electrons determines where reduction occurs and where oxidation occurs. This flow of electrons depends on where we place the positive and negative ends of the circuit from the external power source. The positive end goes on the anode we want to use, and the negative end goes on the cathode we want to use, so that the electrons flow from the anode to the cathode. Our experiment is to reduce zinc onto copper, represented by a penny. We ensured that we could use a penny dated from 1982 or earlier, as these are comprised of 95% copper and 5% zinc, while those post-1982 are comprised of 97.5% zinc and only 2.5% copper. In our experiment, the cathode was the penny, or the copper, and the anode was the zinc. This reaction is slightly confusing to think of because the penny is actually an inert electrode. The zinc is oxidized at the anode, the zinc electrode, and the zinc is then reduced at the cathode, which is the penny electrode. The copper is never actually oxidized or reduced in our reaction. However, we would still use the zinc and copper reduction potentials to calculate the cell potential because we are determining the likelihood that zinc is reduced onto copper. To calculate the cell potential, we can't simply use the equation E standard equals the standard reduction potential of the cathode minus the standard reduction potential of the anode because of the nature of electroplating. Instead, we should use the equation E standard equals the standard reduction potential of the reduction reaction minus the standard reduction potential of the oxidation reaction. It is important to note, however, that while copper isn't actually oxidized in our reaction, we still use its reduction potential for the calculation. Once we plug in these values into our cell potential equation, we will find that the cell potential comes out negative. This indicates that this reaction is non-spontaneous, thus a normal voltaic cell cannot carry out this reaction. We must use an electrolytic cell in order to apply a voltage or a flow of electrons to perform this non-spontaneous reaction. To maintain electric neutrality, we must provide an electrolyte or a salt so that cations from the salt can move to the negatively charged cathode, and so that anions from the salt can move to the positively charged anode. In our experiment, we used sodium chloride, or NaCl. Additionally, since H2O has a lower reduction potential than that of copper and zinc, H2O has a lower tendency to be reduced by the electrolytic cell, so we shouldn't have to worry about the production of hydrogen gas. First, we clean the penny with rubbing alcohol to ensure that no other substances are oxidized or reduced in our reaction. Next, we added 1.0 molar NaCl to our beaker to serve as the electrolyte which will maintain the electric neutrality in our solution. Next, we weigh the initial mass of the penny, which will be important later. This mass was 3.091 grams. We placed the electrodes, which were the zinc strip and the penny, into the solution and proceeded to perform our experiment. We connected the positive end of the circuit to the anode, the zinc electrode, and the negative end of the circuit to the cathode, the copper or the penny electrode. We turned the voltage up to 12 and turned on the battery, and after 4 minutes weighed the final mass of the penny with the electroplated zinc. This mass was 3.097 grams, which demonstrated that the mass increased from the initial mass of the penny. The change in mass of the penny was only 0.006 grams, which is much smaller than a real electrolytic cell performed under better conditions would have electroplated. Errors in our electrolytic cell that could have lowered its efficiency include an inaccurate measure of the mass, an inconsistent current applied, and the oxidation and reduction of other substances that weren't supposed to be part of the reaction. To further improve the penny's aesthetic, we placed it on a hot plate in order to heat the penny. Doing this would combine the zinc and the copper under the zinc to form an alloy of zinc and copper. This alloy is known as brass. This should make the penny have an almost gold appearance. Electroplating, the focus of our experiment, occurs when a metal from the anode is oxidized to form cations, and these cations are reduced at an inert cathode, forming a thin metal layer over the object. Electroplating objects with chromium, nickel, gold, or silver improves their aesthetic. Electroplating can also be used to prevent or reduce corrosion of a substance. Electroplating certain substances, such as tin, onto a metal, such as iron, that is easily oxidized, can produce a coat that is resistant to corrosion. Some metals, such as aluminum, sodium, calcium, and magnesium, do not exist as pure metals in nature, but rather in compounds such as oxides. This is because the formation of these compounds is spontaneous. Since electrolysis can carry out non-spontaneous reactions, it can be used to separate these compounds into their original substances. Electrolysis helps reduce the compound in order to separate the metal from the rest of the compound. The electrolysis of water can produce hydrogen gas at the cathode. This hydrogen gas can be used as fuel to power fuel cells. Improper disposal of certain hazardous metals produced by electrolysis can be dangerous to the environment. Additionally, untreated wastewater from electroplating factories may contain harmful chemicals that end up in farmlands and community water supplies. In particular, cyanide and acid-based solutions used as the electrolyte in an electrolytic cell can be dangerous if not disposed of properly.